Okay, ever wondered what's really happening when you see water boil? Or how the smell of, say, freshly baked cookies can fill up a whole room? Well, believe it or not, there's a single, kind of secret rulebook that explains all of it. And today, we're going to unpack that rulebook, the kinetic particle theory. So check this out. This picture right here, that's liquid nitrogen. Now, normally, nitrogen is just an invisible gas all around us. But when you cool it way, way down, it becomes this liquid, and get this, it shrinks to take up 700 times less space. I mean, how is that even possible? How can something just shrink like that? Well, the answer is in a world that's way, way smaller than you think. All right, so what is really happening here? To get what's going on with big stuff we can see, like that cloud of nitrogen, we have to zoom in. I'm talking way, way in. We need to go down to the invisible world of particles, because that's where all the magic really happens. So here it is, the big idea. You ready? Everything. And I mean everything. The phone in your hand, the air you're breathing, even you. It's all made of these super tiny particles. And here's the kicker. They are never, ever still. They are constantly moving, jiggling, and vibrating. And that one simple fact, it's the key to understanding, well, pretty much everything. Okay, so let's dive into the secret world of these particles and talk about solids, liquids, and gases. You might be thinking, wait a minute, if everything's made of the same tiny particles, why is an ice cube solid but water is a liquid? Great question. It all comes down to just two things: how the particles are arranged and how much they're moving around.
First up, solids. Take a look at this. See how all the particles are packed super tight in these nice, neat, orderly rows? Think of it like a perfectly arranged classroom. Everyone's in their assigned seat, they can't get up and walk around, but they can fidget. They just vibrate right there in their spot. And that rigid, locked-in structure is exactly why a solid holds its own shape.
Okay, now for liquids. The particles are still pretty close together, but look, it's a total mess now. It's disorderly. Let's go back to that classroom analogy. This is like when the bell rings for a short break. People are out of their seats, they're milling about, sliding past each other. That's why liquids can flow and take the shape of whatever container you pour them into. But notice, they're still crowded in the room, right? That's why they still have a fixed volume.
And last but not least, we've got gases. And wow, look at the difference. The particles are super far apart from each other. To finish our school analogy, this is recess on the big playground. Everyone is just running around like crazy in totally random directions with tons of space in between. And that's why a gas has no fixed shape and no fixed volume. It just expands and expands to fill up literally any space you give it.
So, this table really pulls it all together. It's a great summary. You can see the whole story here. As we go from solid to liquid to gas, notice the patterns? The particles go from orderly to messy to completely spread out. And their energy, what we call kinetic energy, goes from low to medium to super high. And here's a really cool one: compressibility. You can't really squash a solid or a liquid, right? Because their particles are already packed in tight. But a gas, it's mostly empty space, so you can totally squeeze those particles closer together. Easy.
All right, so we know the difference between states. But how do you actually change from one to another? How does something transform? Well, energy changes everything. If you want to melt an ice cube or boil a pot of water, you need to change the energy. It's that simple. It all comes down to energy.
Let's actually watch this happen on a graph. We're going to take some solid stuff, it's called icosane, and heat it up. So we start adding heat, and look, the temperature goes up. Makes sense, right? A to B, no surprises. But then, look what happens. From B to C, the line goes totally flat. We're still cranking up the heat, we're still adding energy, but the temperature just stops rising. It's stuck. So what on earth is going on here?
Well, that flat part of the graph has a special name. It's the melting point. This is the exact temperature where the solid starts turning into a liquid. For this particular substance, it's 37 degrees Celsius. You see the same thing with ice, right? Its melting point is 0 degrees Celsius. The temperature of a cup of ice water will stay at 0 until all the ice is gone. So here's the really important part. Why does the temperature get stuck? Because all that heat energy we're adding suddenly has a new, very important job to do. Instead of making the particles vibrate faster, that energy is being used to break the bonds holding them in their tight, solid formation. It's like the energy is focused on one mission:
snapping the connections between particles so they can finally break free and start to slide around as a liquid. And guess what? The exact same thing happens all over again when it's time to boil. So, once everything's melted, the temperature of the liquid starts to climb again. But then, bam, we hit another flat line on the graph. And you know what that is, right? That's the boiling point. And just like before, the temperature stops rising because every bit of energy is now being used to break the remaining forces, letting those particles escape completely and fly off as a gas.
Okay, so particles move, and that's how states change. Got it. But what about particles moving through other things? This brings us to another everyday mystery. How do smells actually travel from one place to another? Well, the science for that is called diffusion.
I want you to picture this. You drop a tea bag into hot water. You don't stir it, you don't do anything, but you can watch as the color just spreads out all on its own until the whole cup has changed color. Why does that happen? It's the same reason you can smell perfume from across the room. What's going on?
The answer is diffusion, and it's actually pretty simple. Remember how particles are always moving randomly? Well, because of that, they have a natural tendency to spread out. They move from an area where there's a lot of them, a high concentration, to an area where there are fewer of them, or a low concentration. They just keep spreading and spreading until they're all mixed up evenly.
So, let's turn this into a particle race. Does everything diffuse at the same speed? Absolutely not. Just like in any race, some particles are way faster than others. And it turns out we can predict who wins. The speed of the race really comes down to two main things: temperature and how heavy the particles are.
First up, temperature. This one's easy because we already know the rule. Hotter means more energy. More energy means the particles are moving around way faster. And if they're moving faster, they're going to spread out and diffuse much more quickly. It's exactly why you can smell a hot, simmering stew from the other room, but you'd have to stick your nose right in the bowl to smell it once it's cold.
The second big factor is just how heavy the particles are, their mass. Think about it this way. If you have the same amount of energy, is it easier to push a bowling ball or a tennis ball? The tennis ball, right? It's the exact same idea with particles. The lighter particles are like the tennis balls. They zip around much faster than the heavy bowling ball particles. So lighter means faster diffusion.
And if you want proof, look no further than this classic experiment. It's brilliant. On one side of this tube, we have ammonia gas. Its particles are pretty light. On the other side, hydrogen chloride gas. Its particles are much heavier. They start diffusing towards each other, and when they meet, they react and form that white ring you see. But look, where did the ring form? It's way closer to the hydrogen chloride side. Why? Because the light, speedy ammonia particles raced down the tube and traveled much further before the heavy, slow ones could meet them. That's a photo finish, and it's perfect proof.
So let's step back and look at the big picture. All these things we've talked about, melting, boiling, freezing, even diffusion, they're not just a bunch of random facts. They are all parts of one giant connected system. It's all governed by particles, their movement, and energy. You can see here, the red arrows show when you have to put energy in to break the particles apart, like from melting and boiling. The blue arrows show when energy gets released as particles come back together, like in freezing. It's all one beautiful, logical cycle.
All right, to finish up, I'm going to leave you with a little puzzle to chew on. Imagine you spill a drop of water on a table, and right next to it, you spill one drop of perfume. You smell that perfume almost instantly, right? But that little puddle of water seems to just sit there for ages. Why? Using everything we've just talked about, evaporation, which is like boiling but slower, the mass of the particles, and diffusion, why the huge difference? The answer, as always, is hidden in the secret world of particles.